So, let us resume our discussion on limestone calcined clay cement. We were talking about the fact that limestone is increasingly being used as a cement substitute in different proportions, sometimes as an additive, as a performance improver to regular Portland cement, or sometimes as a replacement for cement in larger proportion that leads to the development of Portland limestone cement. But what we also discussed was when limestone is used in combination with reactive alumina, it gives an entirely different perspective to the early hydration chemistry that actually takes place in such systems. So, these are ternary blended systems where we not only make use of pozzolanic reaction of the silico-aluminate mineral admixtures, we also make use of the carbonate aluminate reaction that happens because of the limestone and the reactive aluminate that is contributed by your mineral admixtures. So, that way you get a system that fills up pore spaces very early in the process, and we saw that the best kind of materials that were suited for this purpose were the ones which had a high amount of reactive alumina, right. So, calcined clay is probably the best SCM for this purpose, and we saw that with this kind of a system you do not necessarily have to have a very pure kaolinite. Okay, when you have a very high content of kaolinite like 90% and above, you are talking about products like metakaolin, which could be quite expensive. So, what we would like to do is utilize the waste clay reject material that is available at the quarries or the mines where they are getting kaolinite out for other industries like ceramics and paints. So, in those cases the clay which has a kaolinite content of 40 to 60%, as small as that, is suitable enough to be used as ingredient in the ternary blended limestone calcined clay cement. So, effects of limestone obviously we have seen this earlier, are towards the physical packing effect that you get as a filler, as well as a chemical effect that you get when it reacts with the aluminate. Interestingly, there are several limestones which are considered to be unusable by the cement industry, right. When you have limestone which is lying as a reject in the cement industry, much of that is simply getting dumped and not really being utilized for cement manufacture. Even if it has to be utilized, what the cement industry has to do is get very pure grades of calcium carbonate to add along with this impure grade of calcium carbonate, so that they get an overall formulation that is suitable for cement manufacture. However, if you can find alternative uses for this limestone, it can really make a lot of sense. So, people have explored the use of this waste limestone from cement industry, as well as there are other marble dust which can also contribute to calcium carbonate, okay, or Kota stone dust. Again, you know that the stone processing industry in several parts of the country produces lots of wastage. Now, even if you look at the granite quarries which are doing granite slabs or the Kadapa slate slabs, the amount of wastage generated could be as high as 80 to 85% in many cases. That means they are only utilizing about 20% of the material properly. So, this wastage is often available as dust, and when you are talking about limestone based materials, the dust could be quite useful from a perspective of limestone calcined clay cement. So, there is evidence to show that any form of carbonate source can stabilize the ettringite formation at the early stages and prevent its long term conversion to the monosulfate phase. So, again here this figure is showing the amount of ettringite present in LC3 blends with stone dust. So, this here is with a specific type of LC3, and again with other types of stone dust you are again stabilizing the amount of ettringite that is actually forming. So, ettringite is not really reconverting to monosulfate in this case. This diagram here is with quartz. So, that is what is marked LC3 quartz. That means instead of limestone they have used another inert filler like quartz. So, you are not really getting that reaction that you expect with limestone and aluminate from the SCM in that case. So, you only have unreactive crystalline silica in quartz, which is not really doing anything like that. It is probably only doing the filler effect to some extent, but not really the chemical effect that you expect with limestone. Okay. So, with all the grades of limestone, whether it is Kota stone dust or regular limestone, right, all these are actually leading to stabilization of the ettringite that is forming at the early stages. That means it is not converting back to monosulfate. Now, in terms of durability performance, LC3 has been shown to have excellent durability, particularly with respect to chloride binding capacity. Okay. So, as a result, if you look at the chloride diffusion results that are presented on the left side of this graph, if you look at the data for Portland cement, it shows that a fairly high content of chloride exists way into the depth of the concrete member. Whereas, when you do the same with concrete that is having 30% metacoulin substitution of the Portland cement, you substantially bring down the extent of chloride ingress into the concrete. And further, when you are using limestone and calcined clay as combination, you are actually getting this down further to a much lower chloride diffusion characteristic for your concrete. That means you are improving by several orders of magnitude the chloride binding characteristics that leads to an increase in the chloride resistance of the concrete. Okay. So, once again this is the porosity expressed in terms of the pore radius. So, this is basically the graph that you get when you do the mercury intrusion porosimetry study that we talked about earlier. So, here as you put more and more pressure on the mercury, it keeps intruding smaller and smaller pores. So, the pore radius is decreasing in that direction. That means you are increasing the pressure in that direction, the same direction. So, as you increase the pressure, more and more of the pores start getting filled up, okay, because with higher pressure the mercury will be able to intrude into smaller pores. Okay. So, what you see here is that as compared to ordinary Portland cement, the pore sizes that you see with the metacoulin substituted blends as well as the LC3 are much smaller. That means you need to actually exert more pressure on the mercury to intrude those pores. That simply tells you that your system with limestone calcined clay cement will end up having a much lower porosity and lower pore size distribution. Okay. So, overall you get a much more positive influence on durability. Now, again this is a result that is produced at our lab, and again it shows the same kind of trend or same kind of scenario, and here the comparison is made not just with OPC, but also with a 30% fly ash replaced mix. So, you know that fly ash does not really perform very well at the early ages, it requires some time before which it can actually show the true pozzolanic potential. So, at 3 days you can see very clearly that OPC itself is finer than the fly ash system, okay, and LC3 is much finer. So, you get a highly refined pore structure as early as 3 days. Okay. If you compare 7 days, the fly ash is coming closer and closer to the OPC, and by 28 days the fly ash is almost better than that of the OPC, but LC3 continues to be, the green line is the green curve is representing LC3, it continues to be showing a very fine pore structure. Now, of course, the shift in pore size is steady in the OPC system. You expect that as the rate of hydration slows down after 7 days, your pore sizes are not going to change that much after 7 days. Okay. From 7 to 28 days, again going back to the previous slide, the OPC system still had the same sort of a critical porosity that it had at 7 days. The pores were not really reducing in size. Okay. Overall porosity may have been coming down with extra hydration, but the critical size which has to be intruded by the mercury to completely penetrate the system, that critical size is getting reduced as the age of hydration increases. With LC3 you see that at 3 days itself you have a fairly fine size of pores, 0.1 is the critical pore entry diameter, 0.1 micron, that is about 100 nanometers. When you come to 7 days, this comes down to about 0.09 or 0.08 or something like that. Okay. But then between 7 and 28 days, again with LC3 there is not much of a change, you do not see much of a refinement in porosity. That means most of your reactions are nearing their physical completion, practical completion at 7 days itself. Now, again please remember, your Portland cement paste system is a system which can continue to grow or can continue to hydrate as long as there is space available for more hydrate products to fill up. Once the space is restricted, you can't really form and nucleate these hydration products, which will further keep on refining the pores. On the other hand, with fly ash concrete, you know very well that the pozzolanic reaction is much slower, because of which there is substantial increase in the or substantial reduction in the pore sizes from 7 days to 28 days in the case of fly ash. And possibly when you extend the curing to 90 days, you may even see that effect quite strongly with respect to fly ash based mixes. Okay. So, again what we have seen is the microstructural development in terms of mercury intrusion porosimetry. This diagram is actually showing you the system in terms of the measurement of conductivity. Once again, conductivity is because of what? Because of interconnected porosity once, and then second is the ionic concentration of the pore solution. So, once again when you have LC3 or any mineral admixture based systems, you end up reducing the interconnectivity of the pores. So, you expect the conductivity to come down anyway, and further with systems like LC3 or like silica fume for instance, you are also going to trap the alkali ions, thus reducing the pore solution concentration, and because of that you expect that the conductivity drop is going to be quite drastic at very early ages itself. So, all these green curves are basically your limestone calcined clay systems. The fly ash system, just because it hydrates much slower, tends to start dropping its conductivity significantly only beyond about 28 days of hydration, whereas the OPC system has stabilized even after about 10 to 14 days of hydration. Okay, again this is showing the same effect with fly ash, with OPC and with LC3. So, this is an interesting cartoon that you can show. So, you have your LC3 which is making up the tortoise in this tortoise and hare story, sorry, which is making up the hare in the tortoise and hare story. But of course, in the story the ending is a little bit different. The tortoise wins and the hare loses. Here the tortoise is losing because it is slow, because LC3 is faster getting to the cache, right, that is what is at the end. Okay. There is more cache available. Again, this is similar result, so I am not going to talk about this in more detail. Now, what happens is the interconnectivity of the porosity that determines the conductivity of the system can be converted to something called the formation factor. Okay. Now, the formation factor is also known as the effective diffusion coefficient. So, please remember your concrete is basically a mixture of interconnected network of pores and then solids around these pores. Okay. So, there when you try to conduct charge through this concrete, the conduction will primarily happen through the interconnected porosity, but then your solid phase also can have some influence on that conductivity. So, based on the interconnectivity of the pores and how straight or how tortuous these pore systems are, you will ultimately get an effective conductivity which you can use to calculate this formation factor. So, formation factor is nothing but the conductivity of the system divided of the pore solution divided by the effective conductivity of the system. Okay. So, the formation factor being low implies that your conductivity of the system is influenced mainly by the conductivity of the pore solution, right. If you are having a very high formation factor, it implies that the conductivity of the system is extremely low irrespective of the conductivity of the pore solution, right. Did you get my reasoning there? So, this formation factor is the ratio of the conductivity of pore solution divided by the conductivity of the system, the overall system. So, if the overall system has very low conductivity, irrespective of your conductivity of the pore solution, the formation factor will be high. So, when the system has very low conductivity, what does that mean? It has got much better resistance to penetration of aggressive fluids. So, the higher the formation factor, the better is your concrete with respect to durability. Okay. Please remember that the conductivity experiments were done on cement paste, and the formation factor which was actually taking in inputs from the conductivity measurement was again determined on cement paste, and this will later be applied to understand what would be the potential durability of these concrete systems. So, again as compared to OPC, your LC3 is at a completely different level of formation factor. Of course, FA30, the 30% fly ash replace mix at 28 days, it is not that much different from OPC, but by 90 days there is significant additional hydration that leads to a much higher formation factor. So, now how does this formation factor work? The formation factor seems to be a much better indicator of your water filled porosity than the bound water content. So, this is actually plotting the water filled porosity in the system as a function of the bound water content. Please remember, bound water, we talked about the fact earlier that this is the water that is bound to the structure of the hydration products. More hydration, more bound water, okay, right. So, as more and more hydration happens, you expect the porosity or interconnected porosity to reduce, right. So, with increasing bound water content, you expect that your water filled porosity is going to keep coming down. But unfortunately, what happens is when the binders are different, like your OPC binder or your fly ash 30 binder or LC3 binder, your results are quite different. I mean, there is no clear dependency, there is no single dependency on this. But when you use formation factor, you get a much better relationship with respect to all concrete mixes, all mixes irrespective of the type of binder. Okay. So, you see here porosity is plotted as a function of the formation factor, and you see a much better correlation between the results. Of course, this is not a linear correlation, but still you have a very good quadratic or rather exponential fit in this case. Now, when you use this sort of an equation, what you can effectively end up doing is understand the influence of formation factor on the durability parameters, and that can be done further
with the help of this expression called the Katz-Thompson expression. So, here the permeability coefficient K, which is also called the intrinsic permeability, that means you are expecting this value to be there in the system. Intrinsic permeability of the system is given as 1 by 226 times the formation factor multiplied by the square of the critical diameter. Please remember, we talked about mercury intrusion porosimetry where we pick up this critical diameter. So, you use this equation to get an expression called intrinsic permeability. Now, obviously, when the intrinsic permeability is high, your concrete permeability is expected to be high. When the intrinsic permeability is low, your concrete permeability will be expected to be low. So, again here, as you see very clearly, as you come from OPC to FA30 to LC3, there is a drop in the intrinsic permeability. The question remains whether this will translate into a better durability performance or not. So, for that obviously you need to do extensive studies. So, we actually have performed studies on different types of concrete. You have M30 concrete, M50 concrete, and a concrete which was designed with the same binder content and water to binder ratio. So, please remember M30 and M50 could mean different water cement ratios based upon the type of binder. So, for example, compared to OPC, you may need lower water cement ratio to get the same grade of concrete when you use fly ash. Okay. So, this M30, M50 is basically with OPC, fly ash 30% and LC3 mix, and with the M50 of course you can see very clearly there is a difference in the binder contents, significant difference in the binder contents. In the case of M30 you have the same binder content, but some difference with respect to the water cement ratio that was needed for the fly ash based mix. For LC3 there was no need to change that. In fact, for M50, for the type of LC3 that was produced in this, you could actually use the same water cement ratio as the OPC mix, but you needed lower binder content as opposed to the OPC mix to obtain the same grade of concrete. Now, the common mix had 360 binder content and 0.45 water binder ratio. So, here we were working with 3 different binders. We designed 3 concrete mixes, one based on 30 MPa grade, one based on 50 MPa grade, and one based on a common binder and water binder ratio grade. Let us see how this works. The strength evolution, there is not much different ultimate strength, but what you see is your LC3 and OPC systems are obviously obtaining strengths much faster than your fly ash systems. That is again expected, it is not really something surprising. In terms of the common mix, when you compare the same binder, LC3 appears to be marginally higher than your OPC and fly ash based systems, marginally higher. I mean, I would not say it is very high because the difference is less than 10 megapascals out of a strength of nearly 60 megapascals. So, I am not going to really talk about that as being a major. So, this is actually strength development all the way up to 1 year. So, fairly long term performance has been collected in this case. But more importantly, we have to look at the results of the durability parameters. So, once again, surface resistivity, which we saw earlier with fly ash and slag based mixes, as to how they compared with OPC, we saw that you needed, you could actually get the resistivities to be a very high level when you replace cement with 30 or 50% slag or fly ash. Now, in this case, the comparison is totally different. With OPC, your resistivities are more in the range of 10 to 20 kilo ohm centimeter, okay? Whereas with LC3 concretes, you are in the range of several hundreds kilo ohm centimeter. Now, this has a major significance with respect to corrosion propagation. If your concrete is highly resistive, that means an inverse of conductive, then the flow of ions through your concrete medium is going to be highly restricted. That means your corrosion propagation will be affected severely. So, in other words, LC3 system is expected to have a very positive influence on corrosion propagation. Okay. Now, when you look at RCPT, rapid chloride charge passed, your Portland cement concrete is in this range, always around 2000 coulombs, 2000 to 2500 coulombs. Whereas, your LC3 systems are in a range which was previously thought to be achievable only with silica fume. Remember, I talked about the fact that silica fume gives a very positive result with respect to RCPT. LC3 can give you even a better result with respect to RCPT. So, you see here that you are obtaining extremely almost negligible permeability as per the scale suggested by the ASTM test method, which actually looks at the RCPT test. Similarly, the chloride migration test, another electrical potential applied test where you are measuring the depth of chloride penetration and converting that to an effective diffusion coefficient. You see again the LC3 system seems to have a much better performance as opposed to the OPC or even fly ash based systems. Okay. So, again the results across the board show that the chloride resistance characteristics of LC3 based concrete are far superior to that of OPC concrete and definitely better than even the fly ash concrete. Now, again sorptivity is the unidirectional absorption by capillary action of water through the system. So, once again with LC3 you see the sorptivity values are generally lower as compared to ordinary Portland cement, okay, irrespective of the type of mix that has been tested. So, once again it is not just with respect to the conductivity, we are also looking at direct water absorption, and that also shows a positive result with respect to LC3. Oxygen permeability is presented here in terms of an index. So, the permeability coefficient is typically of the order of 10 to the power minus something, right. So, when you take negative log of that, you get a positive number. So, the lower the permeability, the higher will be the permeability index, because you are taking a negative logarithm of that number. So, again with fly ash and LC3 systems, there is a distinct advantage over the OPC system with respect to gas permeability also. So, what does this mean? That your resistance to carbonation or carbon dioxide diffusion may be higher because of the pore structure. Okay. But what does the result of the carbonation show? That is more important for us to understand. So, again once we get there, again pore structure, once again for concrete it is reflecting the same kind of result that you get for cement paste. So, I am not going to talk in detail about this. Bulk diffusion again is a chloride diffusion, which we talked about previously, and I already explained to you the results that were obtained in the first few trials with LC3. Again here also compared to OPC, your system with LC3 and fly ash, because here the concretes were actually hydrated for 1 year, cured for 1 year and then tested for chloride resistance. That means at 1 year potentially all fly ash that has to react would have been reacted. There is no question of more fly ash reaction after that. So, potentially the structure has been developed completely and there is generally no difference between your fly ash concrete and LC3 concrete. Now, again this is showing you the bulk diffusion for the concrete mix, which had similar binder content and water binder ratio. So, at that level you see that the LC3 actually is able to give you better performance than your fly ash based systems. And needless to say, anytime you substitute OPC with mineral additives, your chloride diffusion will definitely be better, but the extent of difference is much better with LC3 systems. Now, the important part is how does this actually perform in the real field. So, we were not just testing specimens that were cast and cured in the lab, we also cast slabs which were then used to remove cores from the slabs, and these cores were actually examined for their durability potential. So, again here this is the slab which is being cast, and these are cores that have been removed from the slab at different ages. So, what I am presenting here is a snapshot of the result that was obtained. So, with LC3 compared to the lab specimens which showed a charge past of 120 coulombs, the field specimens were still able to show a charge past of only 160 coulombs. That means there is not much difference between the lab cured and field cured specimens. Even your steady state, non-steady state diffusion coefficient is not really different by much. Your oxygen permeability is almost the same, only the sorptivity index is a little bit different. The absorption, capillary absorption of moisture is a little bit higher for the field specimens, but for all the other conditions your system is performing nearly the same as the lab cured concrete. Lab cured means 28 days lab cured, field cured means what? 7 days moist cured and then exposed to the atmosphere. So, you get nearly the same performance, okay. But with PPC, here it is a 25% fly ash replaced concrete mix. Look at the difference between the lab and field specimens, major difference is there, okay, except for oxygen permeability, which is not really capturing that difference very well, but especially with respect to the charge passed and the non-steady state diffusion coefficient, your gap is very large. This means that concrete with LC3 may not be very sensitive to the differences in curing that occur in the field. So, for example, if you are curing OPC concretes for 7 days, you can continue to cure your LC3 concrete also for 7 days. You do not need to do extended curing like you need for PPC or fly ash based systems. Again, this is just explaining the result in words, so I will leave that to you to understand. Unfortunately, I do not have the result for carbonation in this presentation, but I would like to tell you that in general with respect to carbonation, the performance of LC3 is poorer as compared to OPC or even fly ash concrete. Now, when you compare the same binder content and water binder ratio, the carbonation rate of fly ash concrete and LC3 concrete is not much different. But nevertheless, both these concretes are poorer as opposed to ordinary Portland cement concrete. We already discussed why that should be the case, because you have less lime availability in the system. In LC3 you have much greater chance of most of the lime getting depleted. That is because all your reactions, the pozzolanic reaction, the carbonate reaction, everything involves lime. So, a lot more lime consumption is happening in the LC3 system as compared to your fly ash based or slag based systems. So, you can expect that there is definitely going to be a reduced resistance to carbon dioxide penetration. Now, the question is whether that actually leads to carbonation induced corrosion, and we discussed that will depend a lot on the availability of moisture. If moisture is restricted, as we expect to be the case with LC3, you may not really have a condition of corrosion even though carbonation depth is greater. Okay. So, that is enough to discuss about LC3. Now, we will look at some more interesting admixtures that can be used more from the local perspective. So, we saw LC3, limestone is available wherever cement is available, right. Clay is mostly available in all parts of the world. So, you can actually make LC3 globally. So, it is one of the global means of looking at reducing the cement clinker impact in concrete. Now, coming from that, we can actually try and adopt more local means of reducing the cement clinker usage in concrete also. And one of the local means is the use of sugarcane bagasse ash. So, the bagasse is basically the fiber that is left behind after you crush the sugarcane and extract the sugar. Okay. So, bagasse, the fibers have very good calorific value. So, they can be burnt quite nicely in boilers, and a lot of heat can be obtained by burning, which can be used for other purposes like conversion of processing the sugar further, or it can be used to generate electricity. So, today it has been mandated by all sugar, it has been mandated by the government that all sugar producing plants which are using sugarcane to produce sugar have to have a cogeneration plant. That means they also need to produce power to satisfy their own requirements. Okay. So, because of that, there is an increase now in the extent of burning of bagasse that takes place, and when bagasse burns, it makes this black colored product called bagasse ash. Okay. For the most part, people are not really concerned with the environment. So, what they simply do is mix this ash with a little bit of water and dump it. Water is added so that the ash does not fly around and create a nuisance, right. So, mostly if you go in the vicinity of sugar plants, most of this ash would be dumped. But what you need to look at is this ash has a very good source of silica, just like your rice ash. There is quite a bit of silica that is present in bagasse ash, nearly about 70% silica content can be available in your bagasse ash. So, that could be a useful resource as a pozzolanic material. In India, it makes a lot of sense because India ranks second in the world in terms of sugarcane production after Brazil. If you look at literature in bagasse ash, you will see a lot of literature coming out of Brazil, obviously because it is available there in plenty, then India, Thailand. So, these are the countries that produce a lot of bagasse ash or bagasse. Okay. So, in India, 47,000 tons per day of bagasse ash is produced, and it is available for usage, but it is mostly getting disposed. Now, if you convert that to a yearly figure, what do you get? 47,000 tons is how many in terms of a year? If you convert that, multiply by 365, what do you get? Or let us say multiplied by 300. Let us say 50,000 into 3 is 150,000, 150,000 tons into 100. So, we are talking about 1.5 million tons per year, 1.5 million tons per year. How much fly ash is generated per year? 250 to 300 million tons of fly ash. How much cement is manufactured in India per year? About 300 million tons. So, fly ash availability is nearly the same as the extent of cement manufactured in India, but bagasse is only showing up to be 1.5 million tons. But it may make sense to have bagasse or bagasse ash in the areas where the cement production relies heavily on fly ash for production of PPC. So, when fly ash is not available, a useful alternative source for that ash content could be bagasse ash, but then we need to be convinced whether this material can perform as well as fly ash or not. So, that is why we undertook a very large research study, but before that, of course, you can see here that the concentration of sugar plants is in some states. Okay. So, here you have basically in the Indo-Gangetic plain, you have in Maharashtra, in Tamil Nadu and Karnataka, that is where you have most of the sugar plants located, and you can see here the bagasse availability in tons per day has been plotted, and there was an extensive research program that was conducted here by one of my previous PhD students, and he continues to work on this, and what he has done now is produced a GIS enabled map which can actually explore which can actually tell the cement plant what is the nearest availability of the ash, whether it is fly ash or bagasse ash, based on a GIS based network. So, that way the cement companies can actually utilize it to determine what would be a useful substitute for them to make the PPC. Okay, but once again the proof of the pudding, as I said, always is in the eating. So, is the bagasse ash suitable for use in concrete? For that you need to test its properties through a systematic characterization and understanding how it actually affects the concrete properties. So, with respect to OPC, the primary difference with bagasse ash is that it has got very high silica content, which is quite similar to that of fly ash. Overall, on an average, people have reported 60 to 70% silica in the bagasse ash. Now, I was also talking about the fact that these agro based ashes could have higher alkali contents also. So, you need to be a little bit careful in exploring how this system will affect the alkali silica reactivity in case you have a siliceous reactive aggregate that you are using in your system. So, you may also have some sulphate that is coming from the bagasse ashes. So, again you need to be careful about how this will overall affect the performance of your system. So, now what we tried to do next was to look at when we collect this bagasse ash directly from the sugar plant. Of course, it is in a wet state. So, it needs to be dried first. So, you have to spend some energy to get rid of the water, or if you can improve the collection procedures, you can collect it directly from the boiler without really wetting it. Okay. So, here it is collected in a wet state and then dried, and then we try to explore the particle characteristics of the fly ash of the bagasse ash particles. So, under the microscope, bagasse ash seems to be a mixture of different types of particles. So, you have fibrous particles which are quite similar to what you have at rice ash. So, what is a fibrous particle? Unburned carbon, organic particles. These are the organic particles which are remnants of the sugarcane which are still remaining in the system. You have these irregular particles like this, which are the most important ones from the reactive silica perspective, because these irregular particles are the ones which give you the reactive silica. You also have spherical particles which seems to indicate there is some condensation from the gaseous state. Okay. The spheres may be hollow or may be solid, okay, but mostly that shows that some level of order has been obtained in the formation of these spherical particles. And then you have very finely ordered prismatic particles, which seems to indicate that there is some crystallinity also in the system. So, in the boiler, the temperature is typically maintained around 500 to 600 degrees Celsius. Now, of course, you need a very strict control on the temperature to be able to ensure that you have exactly that range of temperatures. Very often, in certain parts of the boiler, you may end up having temperatures which are in excess of 900. So, what happens to silica when you increase the temperature? When you increase the temperature beyond 900, what will happen? Recrystallization may happen, right? To produce the amorphous material, we need some distinct range of temperatures. If you raise the temperature too high, you may end up getting more crystallinity back in the system, which results in a loss of your reactivity in the system. So, when you go to above 900 degrees Celsius, you start forming these sort of prismatic materials which are representing highly crystalline systems. Okay. So, what we then tried to do was look at the characteristics of these individual particles in the bagasse ash. So, we tried to eliminate the fibrous fractions, the coarse and fine fibrous fractions that were there in this bagasse ash. You can see here that the length of these coarse fibrous fractions is more than 10 millimeters, okay, while finer fibrous fractions are probably 3 to 5 millimeters in size. The real particles that are useful for us are obviously the fine burnt silica particles, which are much smaller than that. So, what we wanted to do was explore how best we can utilize the potential of this material without really having the need to process it extensively, because any processing in terms of heating or grinding and all that requires the use of energy. So, any additional energy that you put already starts cutting down the utility of the product, because if you put in more energy, your utility of the product will reduce, because you want to use systems that are waste or byproducts from other industries like fly ash, for instance. So, for it to compare with something like fly ash, you need to produce a system which is where you input very less energy. So, in this case we tried several different methods. We tried, so all these are expressed in terms of the strength activity index. We discussed earlier, strength activity index is simply the strength of the pozzolanic system divided by the strength of the plain Portland cement system expressed as a percentage. Okay. And for fly ash to be deemed to be a pozzolan, this minimum strength activity index should be 75%. Okay. Your fly ash should be at least having a strength activity index of 75% for it to be deemed a pozzolan. So, here we applied the same to bagasse ash and prepared blends with 20% substitution of the cement with bagasse ash, just like you do for fly ash. Okay. If you look at ASTM C1202, that describes the strength activity index test for fly ash, and we applied the same test here for bagasse ash. So, you can see here that the as collected bagasse ash, the raw bagasse ash at 7 and 28 days was falling marginally short of the requirement. Okay. As collected bagasse ash. So, obviously it needs some processing, otherwise you are not really going to get substantial benefits out of it. When we extracted only the coarse and fine fibrous fractions, our performance was really going down tremendously. Okay. That means there is something wrong, we do not want to use those in the concrete at all. So, there has to be some way of getting rid of the carbon. Okay. So, there are different ways. One is obviously burning at a higher temperature. So, instead of 5 to 600, we took the material, we did an extensive burning study. We found that at 700 we could maximize the potential. Beyond 700, because of the reconversion to crystalline forms, the reactivity came down and we lost the performance. So, at 700 when you burn it, you are increasing the pozzolanic activity to more than 80%, that is good. Okay, but then you are giving substantial extra energy input after the material has already undergone a burning process. So, that may not be a viable option at all. We tried a grinding study also. We took this bagasse ash that is collected and kept on grinding it to different sizes. Now, interestingly, what happened was when we started grinding to different sizes, it was the carbon particles that were getting ground. The silica, which was harder than the carbon, did not get ground at all. So, until we ground to a fineness of less than 53 microns, we were not able to make the 75% deadline at all. So, again too much energy is being input and you are not really getting any benefit out of it, because you are simply grinding the carbon, which is of no use. Okay. Now, this is interesting, simply sieving it through a 300 micrometer sieve was able to actually extend your pozzolanic activity index to above 75%. Now, that is an interesting thing, because most of the carbon seems to go out. So, originally this loss and ignition of this as collected bagasse ash was of the order of about 20-21%. After the sieving, it came down to less than 6%. So, that is a major change in the magnitude of unburned carbon that you have in the system. So, what we did further was, after sieving, we said that okay, anyway when you produce Portland pozzolan cement, the ash is interground with the cement clinker. So, let us try intergrinding with the cement, or rather when you intergrind with the cement, you get particle sizes that are similar to the cement. So, let us try grinding it to a fineness which is similar to cement, 300 square meters per kilogram. So, when you sieve it and grind it, you obtain a pozzolanic performance that is more than 100%. That means you are actually able to get even better strength than the plain Portland cement mix. So, that shows that you have very good potential pozzolanic performance in this material. Now, of course, you also get that from burning and grinding. So, 700 degrees burnt material was further ground to 300 square meters per kilogram, right, and that also produced an excellent performance. But why would you do burning when you can actually do sieving? Okay. So, sieved and ground material we saw as the best performing out of all these, and we used this to produce SCBA based Portland pozzolan cement, which was 5, 10, 15, 20 and 25% replacement. Now, again 5% replacement is important from the point of view of the performance improver in OPC. You need to understand what happens when up to 5% material is used. Now, 5 to 20% could be useful from the perspective of blends that you can actually do with other mineral admixtures. At 25%, you want to explore whether it is actually going to produce a significantly good quality of PPC or not, okay, as opposed to fly ash based PPC, which also contains about 25% of fly ash. Okay. So, again I am showing you some performance characteristics. Strength, we saw no difference in strengths as opposed to ordinary Portland cement, almost the same level of performance was obtained, okay, irrespective of the replacement level, from 5 to 25%, no drop in the strength at all. The replacement level here is plotted on the x axis and the charge passed in coulombs is plotted on the y axis, and you can clearly see as compared to ordinary Portland cement, your systems with bagasse ash at least at 15 and 25% show a very low chloride permeability, okay, as opposed to moderate in the case of OPC. And when you replace just 5% of bagasse ash, you are able to bring it down marginally and have a positive influence on the performance. Depth of penetration of moisture, this is actually a test where you have a concrete cube and you apply water pressure and you look at the depth of penetration of the water into the system after you apply the same water pressure for 3 days. Okay. So, this depth of penetration again reduced significantly when increasing levels of bagasse ash were used. Now, interestingly what you see is when you cure for a longer period of time, you again get the benefits of the pozzolanic reaction much better than you get at early ages. So, that is something that we understand well anyway, because pozzolanic reaction is expected to be slower, and in the long term if you continue curing, you are obviously going to get enhanced benefits out of this system. Okay, thank you.